Alright, today's lesson builds on what we did on Wednesday, which was reducing or simplifying a square root with a number on the inside that maybe doesn't reduce all the way down. And the difference between a value that you would have to reduce versus one you would not have to reduce or simplify would be if that number is a perfect square. So for instance, we talked about a the other day, how if you have a fraction, you can split this apart to be the square root of the top and the square root of the bottom separately, and a perfect square is going to reduce all the way down. So the square root of 36 is 6, square root of 64 is 8, and then I would reduce this fraction by dividing top and bottom by 2. Now don't confuse, this is a square root thing. This is just a simple fraction thing. You know, they're both even, they both have a greatest common factor of 2, so when I divide those I get 3/4 as my answer. Now I want to show you just a different way you can do this problem. If you were to reduce this fraction at the beginning of the problem, before you square root, so let's see, what goes into 36 and 64? I think you can divide both of those by 4. And if you do that, you're going to get 9/16. And you can still square root the top and the bottom separately, only we switched our steps, so we reduced our fraction first here, whereas here we did it second. And now we're doing the square root, whereas last time we did it first. And I'm going to get 3/4 right away. Okay, point here is you get the same answer. Now, let's say you split the problem apart in part B, and the top part reduces, square root of 16 is 4, but then the bottom part doesn't. Today we're going to talk about another way to reduce where this gets out of the bottom and into the top. Okay, this is called rationalizing the denominator. That's what we're going to talk about today after we do part C. As well as how to deal with a variable. Now C doesn't have a variable, but that will also be part of, I'll just write it here, plus how to square root a variable. Okay, so that's what we're going to do today. I'm going to go ahead and tell you this is not a finished problem. Not finished. Okay. So let's go ahead and look at part C. The only reason I'm going over part C is because if there is a square root over both pieces, okay, so on A, you can see it goes over both parts, top and bottom. B, top and bottom. But on C, it only goes over the top. So right now my answer should be something that gets reduced, which will break apart over here, over 16. So we need to figure out what's over here to determine what's going to go up top there. So if I reduce 24, just as a reminder, you want to think of the biggest perfect square that will go into that number. Perfect squares are, let's list a few just as a reminder. 1, square root of 1 is 1, but I also told you on Wednesday you're never going to pick 1. There's always going to be a number bigger. Square root of 4 is 2, square root of 9 is 3, square root of 16, square root of 25. Okay, I think you get the idea. And we went all the way up to 144. And the square root of that is 12. So I can break this up into the square root of 4 and the square root of 6. So 4 is in my list, 6 times 4 gives me 24, and this reduces to 2 square root of 6. All right, so if you think back, what was our first thing? We break it apart, we simplify it, but then we have to reduce the fraction. And now you have a mixture of square roots and non-square roots. And these two numbers here are on the outside of a square root. 6 is the only one underneath. So 2 and 16 can be reduced to 1/8. And since the square root of 6 has nothing to reduce with, it stays the same. And this one is finished. Those are our two answers. So let's talk about this problem here that we couldn't finish. Here's what we're going to do. Whatever the radical in the bottom is, okay, so I realize there is a 4 in the numerator. We're going to focus on just the denominator. That is going to be something we need to get rid of. And if you think back, what's the one thing that gets rid of a square root? It's a square. So if I square this, okay, that is to say, multiply it times itself, I effectively get rid of the radical. And again, this is called rationalizing the denominator. A rational number just means it's a fraction, And then the denominator is where we're going to see if we need to reduce, meaning if you have a radical in the bottom, make sure you separate those two words, rational and radical. Rational is fraction, radical are these square root looking thingies. So if we do this to the bottom, let's see, well, if we continue, we get the square root of 4, which is 2. Okay, so the square root disappears. And if you do anything to the bottom, you need to also do it to the top. So if I multiplied by the square root of 2, those are the two places. I need to do that to the top as well. And square root of 2 doesn't reduce. It'll stay the same since 4 is on the outside. We wouldn't want to multiply those and get 8. That would be incorrect. But also keep in mind, if we have a fraction at the end of the problem, we might need to reduce it. 4 and 2 are on the outside, and that makes 2. So this is your final answer. There's another way to do this problem. If you think about what 16 over 2 equals, couldn't you just do the square root of 8? And I could just act like this is Wednesday, and I could break this apart and say, well, the square root of 4 is a perfect, and then 4 times 2 is 8. Square root of 4 is 2, and you get the same answer. Let's try one beginning to end. Yeah, square root of 17 over 5. I chose these numbers specifically because A, you can't take the square root of either one of those. They're not perfect. And B, 17 divided by 5 is not going to reduce like it did in the last problem. So if I go ahead and split these apart, I rationalize, because I have a fraction, the denominator. So I gotta say, okay, I gotta multiply the bottom by itself, or square it. And I'm going to go ahead and just show that every time right at the beginning of the problem. Okay, I wouldn't use the exponent of 2. I would go ahead and just write it like this. And then that will get you the square root of 17 times 5, square root of 5 times 5. If your square root is still in the bottom, that means you need to go further, because remember, the whole reason is we want to get this radical out of the bottom. And this should be easy, right? Because we squared it, it's going to be a perfect square. And there's your final answer. Those are problems where you are dividing. Number 2 is dealing with a problem in which you are multiplying. And we sort of did this in reverse on Wednesday. We would take a single number, like 24, and we would split it apart into a multiplication problem. Well, now it's already split apart and we want to put it back together. And a really easy way to do this is inside times inside, outside times outside. So the inside two numbers are 3 and 3. So we're going to get 9 on the inside, and the outside two numbers are 2 and 5. So we're going to get 2 times 5, 10. The square root of 9, c to the, now you got to remember how to multiply your variables. If there's 2 here and 5 here, that's a total of 7. Add them together. Similar to the last type of problem, after we do everything we need to do to it, there's usually something to do at the end. You need to then separate your numbers and see if you can square root any of them. And I'll tell you this, if it's a number, you'll probably have to split it apart unless it's perfect. And if it's a variable with a degree higher than 2, we need to simplify it. Now here's why I say degree 2. You need to know, when you're dealing with variables, this simple fact. Okay, we've talked about how these cancel each other. It's true when we're talking about solving, they do cancel one another, the square and square root. But the sheer fact of the matter is that x squared being square rooted is x because x times x equals x squared. Just like when you say the square root of 9 is 3 because 3 times 3 is 9. I want to extend this a little bit further though. Let's say you took the square root of a bigger value. Let's say 10. Well, what would that be? Well, let's use the same kind of logic here. When we completed the square, remember they had to multiply and add to a correct value. So when we multiply these together, and remember they got to be identical, somehow I'm supposed to get x to the 10th. So that means these need to be to the 5th power. Okay, and the pattern here is that you're cutting this guy in half. just like you're cutting 2 in half and getting 1. Okay, now the question becomes, how do I do that with an odd number? Well, let's separate this out. Okay, so 10 is just 10 times the square root of 9 is 3, and then we've got c to the 7th. Okay, what I would do is I would think, how many x squareds are in that? There are 3. There's x squared, x squared, x squared. That makes 6, and then there's an extra, right? So you could think of this as these are going to reduce, which is 6 of them, and this one's not. And I call this a remainder. If you have any odd number, that means that 1x is not going to reduce. Go 1 digit lower to your 6, and then cut that guy in half. And your final answer is 30x to the 3rd square root of x. Let's try just one more with a variable. Let's say you have just a regular value, no multiply, and it says 32x to the 5th. Okay, so right away I would break this apart. So you can do the variable separate from the numbers here. And the reason I say that is because the methods in which you do this are very different. With a number, we split it apart. We have to think of a perfect square that goes into 32. I'm going to choose 16. And then the reason is because 16 divided by, that's going to go into 32 evenly, and I need to multiply that by 2 to get 32. So 4 square root 2 times, and then the way we just went over how to reduce with a variable, if it's even, just cut it in half. But if it's odd, you're going to have 1 on the outside. And then I got to think, okay, well, if one of my x's is there, I need 5 of them. That means 4 are over here. And half of 4 is 2. And then I multiply these together, outside times outside, inside times inside. Okay, these are just a few examples. We did 3 bell ringers, 3 examples here. If you have more questions, please let me know. Send me messages, stay on top of things. If you have further questions or you want to see problems done a certain way, you can go on YouTube and Google the name of this assignment, and you will find bunches of videos and ways of people that do them differently. So for instance, there's another way you can reduce numbers like 32. And I'll show you this just real quick, but I don't expect anyone to really do it off of just one example. But they do what's called prime factorization, and that requires you to divide by the lowest prime numbers. So like 2 gives me 16, and you keep doing it until all you have are prime numbers. 1, 2, 3, 4, 5. And you circle pairs, and then the extra ones go inside, and you get the same answer. Now again, I don't expect you to know how to do this, but I do want to give you kind of a little bit of an idea. There are lots of ways to do these, and if my way is not working for you, you might work a little bit more with it. They are kind of complicated, but there are other methods that you might find from another teacher or another video. Don't just think that you have to get all your information from here, guys. Okay, use the internet, use what resources you have, and if you have any questions, let me know. Have a good weekend.